Ready to define some functions on our sample space that is generated when we run an experiment. So remember, we run an experiment and it generates the set of all possible outcomes, which we call the sample space and denote S. All right? And we've seen several examples, but we are now going to define a function that assigns a real number to each outcome in S is called a random variable. So it is a function. A random variable is a function, and we often denote it with capital letters, X, Y, Z, and so forth. So if X is our random variable, it's a function on our sample space to the set of real numbers, assigns it a value to them. Note that in a given experiment, or with and its associated sample space, random variables are not unique. So you can define, in a given sample space, you can define several random variables. So let's look at our classic example. Our experiment is going to be to flip 3 coins. We'll say fair coins. And it generates the set of all possible outcomes, which I'll write here quickly. Heads, heads, tails, heads, tails, heads. Oops. Let's get it. Tails, heads, heads, and then we do the same thing with tails. Tails, tails, heads, tails, heads, tails, heads, tails, tails. So the size of our sample space is 8, and S is the set of all those possible outcomes. So we could define X from this sample space S to the real numbers in such a way that it counts the number of heads in an outcome. Okay, so if you plugged in the argument H, out would come 3. If I plugged in tails, 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 out would come 0. And so we quickly see that X can take on the value 0, 1, if there's exactly 1 head, 2, if there are 2 heads, and 3. So we often represent our random variable by its outputs. So it's a little different than how we might think of function notation in previous courses. We could define on the same experiment and sample space, we're going to define Y from S to R to be count the number of heads minus the number of tails. So that could be our random variable. So Y of H would be 3 minus 0, which is 3. Let's look at another one. Y of HTH is 2 minus 1, or 1. Let's look at one more. HTTH. So that is 1 minus 2, or negative 1. And we see that Y can take on the values negative 3. Let's look at what negative 3 would be. Y of TTT, right? That's no heads minus 3 tails, which is negative 3. Negative 3, negative 1, 1, and 3. So we can define different random variables on the same sample space. Okay, there's 2 types that we will consider of random variables. Discrete random variables, which we will denote DRV. CRV, and continuous random variables, or CRV. So what makes it a discrete random variable versus the continuous? Well, first of all, if the possible outcomes are finite, so if your random variable is finite, so for example, the ones we saw above, if we have x1, x2, some finite number of outcomes, then that's discrete. Or if it is countably infinite. And what does that mean? Well, that means that there exists a one-to-one. So what does that mean? Let's write it down here. There exists a one-to-one mapping from the countably infinite set, which we're saying is X, to the natural numbers. So you could literally enumerate them, such as x1, x2, and so forth, up to forever. Examples of this would be the integers, or the rational numbers, or the even integers. All those are countably infinite sets. And then so if our random variable takes on countably infinite values, then it is a discrete random variable. So the continuous, sometimes it's easier to understand what the continuous is that's not discrete. And this is when x can take on uncountably many infinite values. Oops, I forgot many. So that means we could take it to think of things that we can measure to any degree of accuracy. So examples here would be the set of all real numbers, or even an interval on the set of all real numbers. Often you'll see it with time, distance, length, anything that we could measure to any degree of accuracy is a continuous random variable. All right, we're going to stop there.